Welcome to Scaling Up Success, Key Lessons from Real-World CCUS Projects. I'm Eric Joyce. I'm the Director of Natural Resources, Energy, and Sustainability here at PreScouter, and we're really excited for the topic today, sharing learnings and insights from large CCUS projects, and also an intro to our CCUS database. First off, looks like a lot of the attendees are familiar with PreScouter, but I'll give kind of a quick minute or two. So PreScouter was founded to help help our clients with complex and evolving technology and our market and regulatory areas. We support innovation, new market opportunities, M&A, investments, process improvements, helping our clients both with near-term goals and their moonshot programs, very long-term development. We leverage our experts to provide not just public insights, but also non-public intelligence and deep technical analysis to help them make more confident decisions faster. Over about the last 5 to 7 years, really about half or more than half of our work has been in the sustainability space, helping some of the largest emitters on their road to net zero and other clients with goals just to reduce their emissions. First, again, I know those of you who've been on for a little while, I've said this a few times, but we will be using a Q&A session for about the last 10 minutes of today's call. So please put any questions in the Q&A function at the bottom of the Zoom screen, and we'll try to answer these live today. And anyone's question we do not answer, we will definitely be emailing and answering after the session today. So our agenda today, what we'll do is have our experts share their learnings. First, Mike Monea will share his experience from Sask Power's coal carbon capture plant. He'll share what he's seeing developing in CCS and even the impact of COP28 on some of these technologies and projects. Then Christian, our technical director, will share our database of CCUS projects, technologies, and players, some of the interesting technologies and projects we're seeing, and share some of the ways that our clients are leveraging the tool to make better decisions within the space. Without further ado, first, Christian Salas is a technical director here at PreScouter. He specializes in our natural resources and energy sector, aligning clients with sustainability, efficiency, and financial goals. His expertise in materials, engineering, and science informs his focus on areas like carbon capture and utilization, waste management, biofuels, renewable energy. Christian's extensive experience includes the energy industry consulting, aging management, failure analysis, and technical troubleshooting in special alloys and manufacturing. Mike comes with decades of experience, specifically in carbon capture and storage. Mike is a Saskatchewan geology expert who has helped to revolutionize carbon capture and storage as Sask Power's leader, creating the world's first coal unit carbon capture plant. With professional engineering and geoscience credentials, he has excelled in oil and gas, enhancing CO2 utilization. He's globally recognized, and Mike received the prestigious Green Man Award for his CCS contributions and continues to advance sustainable energy solutions worldwide. Mike, you want to take it away?
Thank you very much, Eric. I hope you can hear me okay. It's a great honor to be able to speak about the Boundary Dam project, and I'm just absolutely flattered that PreScouter reached out and wanted to hear about the Boundary Dam project, and some of the things that we learned by building the world's first commercial plant are to me very impressive. We built, after I built the plant, it went live in 2014. We had issues with the plant, and they were solved. That's what engineers do, and that was pretty amazing. So what we did was we built the Boundary Dam plant, which was nameplated for 1 million metric tons of capture, and that became somewhat less with time due to some of the solvents degrading. And what we found was there's just so many things that we found, but BHP came along and wanted us to form a knowledge sharing group, which we did. And the the BHP is just an impressive global company, and what they wanted to do was to set a platform where, as we dealt with issues from the construction of the Boundary Dam plant, that we would be able to show people realistically what happened and maybe even get some advice from somebody that built a plant somewhere that could help us. And I think that was a very brave way of setting a standard for collaboration around the world. And that happened, and I ran that organization for about 3 years, and then I decided that I wanted to get into deployment of carbon capture and storage rather than just talking about building the Boundary Dam plant. Because the Boundary Dam plant is a post-combustion plant on a lignite coal. And if you can clean up a lignite coal, you can clean up just about anything. And that's what we found with the actual plant itself. So what we did was the total budget for the whole plant would be about $1 billion, $1.2 billion US, or 1.67 billion Canadian dollars. And that included the power island and also the construction of the capture plant itself. So what we did was on the power island, we chose the Boundary Dam 3 unit, which was about 100 130, 140 megawatt plant that was getting ready to be retired. And what we did was we ordered a turbine from Hitachi in Japan that was specifically made for a carbon capture unit. And that turned out to be fantastic. Hitachi not only is a great company to work with, but they, during construction of the turbine, for example, they had an earthquake in Japan. So all of a sudden they said, well, our plant has had severe damage from the earthquake, but they never missed a beat and delivered on time, and a beautiful turbine that worked very well. So we're very pleased with that group. And it's one of the many things that we found in the construction of the site is a lot of good cooperation by different vendors and different facilities that became part of the whole Boundary Dam picture. Now, one thing I'll say is, and I just have this one slide of the Boundary Dam plant. There's a couple things here. One is Boundary Dam is simply a cooling facility for the coal plants. And I know when we went out to bid for carbon capture, a lot of companies in Europe or in Asia felt that it was a hydro plant because it was a Boundary Dam plant. But actually, the dam is just a cooling dam that's made for the lignite coal um, to generate power. But anyway, there's a lot of work that went into Saskatchewan and Canada at that time. We got good assistance from the federal government of Canada in 2008 to 2010. We had $140 million from the Canadian, or 240 million Canadian dollars from the federal government, which was just played a pivotal role in the construction of the plant. So what we did was we also built on the Weyburn project, which was supported by the IEA GHG group and DOE in the United States and various partners around the world put money into the Weyburn project, which became, I think, one of the top peer-reviewed projects in the world. So a lot of that information is shared through the IEA GHG group and also through the International Knowledge Center. So there's so many learnings that came out of the Boundary Dam process, and I do want to talk about them. And I'll give you an example. We were set up for high pressure creation of a very low moisture contented CO2 in order to put in a carbon steel pipeline that would go to the oil fields for enhanced oil recovery. And we also had a backup of saline reservoir, which was very deep, 3.2 to 3.4 kilometers deep, or 3,400 kilometers deep. And that was located very near the plant. So we built, from the Weyburn project, we had all kinds of knowledge on admissibility of CO2 for CO2 EOR, and also the measurement MMV, measurement monitoring and verification process. And we had scientists from all over the world build a team that became fantastic. They not only helped dissect the various components of carbon capture and storage, but they peer reviewed and they studied, and that information is available now. And I welcome you to that. And it's really quite funny actually, because Weyburn's a very small hamlet in Saskatchewan. And people would come, and because the Weyburn project became quite famous, and they wanted to get their picture taken in the town of Weyburn. So there was a sign for the town, and it was right on a highway, a very busy highway in the oil and gas industry. So people would be, standing by a sign and then all of a sudden have to rush away because they might get run over by a truck. So, but the Weyburn became quite famous, and the post-combustion system that we used at the Boundary Dam plant became also quite world known. So we're very pleased about that. But there's one of the learnings, some of the learnings that we had are again posted on the International CCS Knowledge Center website. And one of the big things that we found was is that when we designed the plant, we were geared up um, for a pipeline spec. So it was very low moisture and very high pressure. And what we found later is that there were some very high paying markets that wanted CO2, and that we bought CO2 for, say, fire extinguishers or using in welding and all that were much higher than what the price that we had for CO2 used for enhanced oil recovery or for just storage. And we had no ability to really access those markets because the pressure was so high. So we set up a model where we'd blow the CO2 down in order to get a pressure of 200 psi, say, that could fill a truck or a train rail car, and that just became quite impractical. So when you build these plants, not only is the technology very robust and very good, but you need to also make your discharge of the CO2 in a supercritical state, or certainly in a dense phase state that's available to many different markets, because people want to buy the CO2. So you've got markets that pay for the CO2, which is what we developed in Canada in order to send the CO2 for the Pan-Canadian Cenovus site, which was the Weyburn project. And then there was these higher markets that we could have developed, but the plant was unable to do that. So really, I guess the thing that I would like to share is that we had many issues with the ducting and getting the flue gas analyzed properly. And to be quite honest, we at the engineers at SAS Power, we simply were looking in the wrong direction for what we needed to be equipped for running a chemical plant. So, like for example, we thought that we would be able to run the plant remotely. Well, no, that didn't work very well. So we had to have it, with man or woman, people in the plant on a shift, 24 hours a day, and that was very critical. We had many issues with the plant itself, like the getting the temperature cooled enough. So we had massive heat exchangers that would get fouled because of the we had to also an SO2 issue with the plant. And at that time, we used the Shell Global CANSOLVE system, and they would use a amine in order to take out the SO2. Well, that worked, but it caused issues with the absorber and the other part of the plant that we had. So so many things that we found that we could pass on to you, so that and it's the BHP philosophy. Why reinvent the wheel? Like, say what happened, say what you've learned, and then build a platform for somebody else to take it to another level, because that's exactly what I wanted to do in China, for example. We had many of the Chinese state-owned enterprises come over and watch Boundary Dam being constructed and built. And I remember there's one of the presidents from the Wenong Group came in and he said, "Well, what you're building is great." He said, "But," he said, "it just takes you so long in the West to build anything because of your permits and all the rules and regulations that you have. But your engineering is very good." And he says, "We would like to learn from you." But he said, in China, we don't have plants that are built that we could learn from, and our engineering needs help right now. So we need to work together. And I thought that would be a great idea because again, it's part of this collaboration, which is really the PreScouter model that they have, which is you share information, you learn from it, and engineers will figure out whatever it is that's necessary and needed. So we had many things that we had. Say, for example, the flue gas became critically important for analysis. And what we didn't know is we had a very high concentration of submicron particles, and they were charged particles, and they tended to react with the solvent over 3 to 4,000 hours. So Boundary Dam ran perfectly for 2, 3,000 hours, and then all of a sudden the solvents started loading up, and some of these small products that would be in a parts per billion would concentrate, and they would stay in the solvent, and were not able to be cleaned by some of the reclamation process. So we learned that you need to properly analyze your flue gas, and take a site or a test unit that you can put on that actual site, not anywhere, and not synthesize the flue gas anywhere, because each flue gas is unique, it seems. And that site needs, or that test unit needs to really accelerate the contact time between the solvent and the flue gas. And that's simply all you want to do is instead of, say, hours of contact time where a molecule of solvent reaches a molecule of flue gas, you want to make this into minutes so that you can accelerate the 3,000 or 4,000 hours into a few weeks of testing or a few months of testing. And that way you can evaluate your solvents, which is very important. So what the other thing that we learned very quickly is that vendors have two things. One is they have a solvent, and secondly, they have equipment that's proprietary in your plant. So what you want to do is to make sure that the solvents, that you can assess your solvents from different vendors that make their claims that they can do whatever is needed in order to clean up your CO2. So you can evaluate that on site, and which is absolutely critical. So that is something that we're working on right now. Unfortunately, the test facility that I built at a sister plant, which was only about 4 miles away, or 8 kilometers, or 7 or 8 kilometers away, actually its construction ended up being commissioned about a few months after Boundary Dam went live. So, like, Shell Global used that plant in order to tune or adjust some of the equipment that they had in the Boundary Dam plant. But it really I really needed that plant built earlier. And that was a joint cooperation between Hitachi and Japan and SAS Power. And the relationship again with Hitachi was really fantastic. So what happened was that Hitachi and Mitsubishi combined together in order to develop CCS out of Japan properly. And with the Japanese government, it really worked out very well. It worked out well where the government supported the MHI group or the CCS group in Japan in order to market their product elsewhere. So the other thing that I wanted to talk a little bit about is the on the storage side, we had which sets up my next part of the talk, which will be COP28. But for example, we had both. We had enhanced oil recovery, which was a continuation of the Weyburn project that the IEA GHG supported, and so that went into EOR, and we better understood the I guess the difficulty of transporting the CO2 in a dense phase, and also the companies wanted to recycle as much as they could because it's a product that's paid for. So what they want to do is recycle that CO2 and use it back into their storage. So even back then, we didn't even know what the concentration of the CO2 should be in order to make it effective to work. So we were borderline missable for the CO2 to react with the enhanced oil recovery of a reservoir, right around 1,000 meters to 1,100 meters of depth. And the problem with that is that in storage, you want to get your CO2 into dense phase because you can store so much more CO2 than you can in a gaseous form. So what we learned was that we thought we'd need 92% pure CO2 in order to have an effective enhanced oil recovery program, and it's much less than that. Again, the EOR works very nicely. It sweeps the reservoirs very cleanly. So and governments and oil companies like that because you can make the most effective use of your oil and gas reservoir. You produce your oil, which is in enhanced oil recovery, 30% less CO2 content or greenhouse gas footprint than a primary well. And then you store the CO2 in that reservoir for thousands and millions of tons of CO2. So I remember that when we were when we were working on the Weyburn project, we had risk assessment groups come in and usually they were oil companies, very bright people that talked about deterministic and probabilistic um, analysis on how long the CO2 would stay in the ground. And it's thousands of years, if not millions of years. And what we find is that the CO2 does alter some of the rock somewhat, but it really stores very nicely. So if you have hydrocarbons, you're very lucky because you've got storage potential. And then you've got also oil and gas developments. So you've got a lot of information of the reservoir itself in order to store the CO2. So it's a complete project. I'm going to leave it at there for Christian to talk about PreScouter, and then I'll come back in and talk about some of the implications of CCS coming out of Globe 28 and how CCS can be developed properly. So thank you very much.
Mike.
Perfect. Thank you, Mike. Take it from here and head it back to you now. Let me set up my screen sharing again. There we go. So yeah, again, thanks Mike for the really cool insights about your experience with Boundary Dam, such an emblematic project. And now the next few minutes, what I'm going to talk about is what Eric mentioned at the beginning, a tool that we developed at PreScouter that we see, and our clients as well see a lot of value. We wanted to share that here today, but primarily making focus on a couple of interesting projects around carbon capture, as well as interesting technologies similar to what Mike was telling us about Boundary Dam. So very quickly, an introduction about what our database is. So it's essentially a compilation of projects around carbon capture from the beginning of times, as well as technologies. So all the different technologies, for example, Shell Cancel, as Mike was sharing before, and then their interconnection. So essentially which technologies have been used for different projects, and then we used all of that information to build two more things in the database. One is this dashboard that I'm going to show right now with some of the insights, and then our cost calculator tool that is able to calculate the cost of capture based on different metrics, such as, like Mike was saying, the CO2 concentration in the flue gas, the size of the plant, the location, and things like that. So as I was saying before, in our dashboard, I think it's pretty cool because one could obtain insights very directly. So we have a little bit about the market of carbon capture, how trendy that is. We also provide some information on the project specifications, such as capture size of the different project. And as you can see, the Boundary Dam project, what Mike mentioned, with about 1 million tons per year, it's right about the typical size or the average size of projects that are being developed. And then we're talking about also what the efficiencies we see, what concentration of CO2 in the incoming gas, and what are some of the costs associated with these projects. So on the right-hand side here, you might also see a distribution of projects per industry. So the power industry leading definitely the way here. Boundary Dam, as I said before, very emblematic project in that industry, but there's definitely also a lot of movement in oil and gas, mainly historically, but then we are seeing more and more projects coming on for the chemical industry, hydrogen refining, and many more. We also are able to, with our database, kind of rank the different technology suppliers. As you can see, for example, Shell being one of the top ones with their Cancel technology. That's based on how much experience they have had working on this space for so many years. But then also some other technology types based on also different technology families that you can see here. So most of them still amine-based, but we're seeing more and more membranes and solid sorbents coming to the market. And finally, we have some of the project distribution across the globe. As I said before, we do track almost 700 projects in total, and we classify them with this color coding that is the same as above here, where they are active right now, capturing CO2, feed or pre-feed, under construction, or simply planned here. So what I wanted to share here, a little bit of information around two very interesting projects right now. For that, I'm go to the project database, or the project part of our database, actually, that shows, again, a little bit of the distribution of the project worldwide nowadays. And then we can filter out, say, more information about those different projects. For example, if we go now for a bit to Europe, I know there's a lot of attendees from Europe too. We filter, for example, we want to see what active projects there exist today, what projects are actively capturing the CO2. And I think one of the very interesting industries that is starting more on carbon capture is the iron and steel industry. So far, not too many active projects right now, but definitely some of those that are very interesting. And the one I wanted to talk more today is about the steel and oil project in Ghent, in Belgium. This is a carbon capture plant that is associated with the blast furnace of ArcelorMittal. This is platforms with a capacity of roughly 5 million tons of iron per year. And what this project is doing is essentially taking those waste gases with carbon in it and then converting that into bioethanol. In this case, ArcelorMittal is working with LanzaTech and their technology to convert the CO2 into the bioethanol. And the plant can produce up to 80 million liters of bioethanol, which, to provide some sort of comparison, that's roughly half of the total bioethanol demand of Belgium, for example. So it's quite a impressive project that has actually started producing the bioethanol last month, November 2023, and has been developed for quite some years with some funding, in this case, Horizon 2020. But I do agree with Mike, some of the fundings available for some of these projects, in the case of Boundary Dam, with the Canadian government, in this case, Horizon 2020, make these projects move forward. A little bit about the plant itself, as you can see here. So the red-orange pipeline are the blast furnaces gas. Those go to the compressors and the compressing unit, then the bioreactors for the bioethanol production, and then distillation columns, process water treatment, and digesters as well. As I said before, the first production of bioethanol from this plant happened last month. We do track some of the metrics associated with all of these projects, typically how much CO2 is captured per year, for example, in this case, 135,000 tons per year, and the project cost, as well as what is the destination for the CO2, and finally, who is participating in the project, both the technology supplier, LanzaTech, in this case, with this CO2 to fuels and chemicals technology, and then some of the other participants, of course, ArcelorMittal, LanzaTech, and some of the other members, for particularly in the EPC part. What we provide here is a link actually to our technology database, that other part of the database that I was showing before I moved there to show some of the other technologies. I also wanted to maybe give US a little bit of attention here for people joining for North America. So if we go to the US, there are, of course, also many active projects around carbon capture, as you can see here. And one of the interesting ones, and definitely where there is a lot of attention, is on direct air capture. There are many plants under construction, as well as active projects regarding direct air capture in the US. The one I wanted to emphasize here has to do also with utilizing the CO2 that is captured, and that's the one from Heirloom in Tracy, California. So this is one of the biggest direct air capture plants of the world. It was commissioned, it started operation this year as well. As you can see here, the way Heirloom technology works is by using crushed limestone to absorb the CO2 that's in the air, with around 300-400 ppm of concentration in the air. It is absorbed in the limestone, and then they are using that CO2 with a combination of technology from CarbonCure to mix it with concrete in order for the construction industry. So there's one of the key advantages of the project, of course, is that it works on renewable energy. So it is in order to extract the CO2 from the air and offset some other emissions. Using renewable energy is the key in order not to put more CO2 out there than what is being taken out. And the CO2 that is being removed, those credits are being used by some of the big companies like Microsoft, Stripe, Shopify, Klarna, and the like. These, as I mentioned before, one of the biggest in terms of direct air capture, which is usually smaller in size than some of the power plants, but this one is around 1,000 tons per year of CO2 that is being captured. And as I mentioned before, we provide always the description and some of the details for the technology, as well as who is participating here. And then before I hand it over back to Mike to talk a little bit more about COP28, I wanted to also present the technology database, as I was alluding to before, with LanzaTech technology, Heirloom, and so on. So we do track all the technologies and the technology suppliers. As I said before, so most of them today with liquid solvents as the absorption method, but then we see a lot of solid solvents and membranes coming on. We do also assess what's the maturity of each one of these technologies. There are many now at their TRL 9 of maturity, so commercially mature technologies, but we do also track a lot that are at early stage of developments, because we do want to see what are the new up-and-coming technologies, and that's what I wanted to show also today. So by filtering as per technology maturity, for example, TRL 4, and particularly for very low CO2 concentration, so let's say less than 1%. So apart from, for example, at TRL 4, the Ohio State University technology, the one I want to mention is the one from MIT, because this is a relatively new concept, similar to what I've shown before with direct air capture. The difference here is that in this case, it's direct ocean capture. So instead of capturing the CO2 that is in the air and offset with that some of the emissions, here the CO2 that is being captured is the CO2 that is in the ocean. There are some advantages of doing that. Why capturing the ocean, where essentially there's slightly higher concentration depending on location and depth, slightly higher concentration of CO2 in the ocean, which makes the volume to be cut less. And then typically when capturing CO2 from the air, there is the energy needed to connect the CO2 molecule with material solvent, for example, and then the energy to disconnect that back. In this case, only the latter is needed, so essentially reducing the energy consumption of the process. The MIT technology works by taking the seawater to what is called a first cell. That essentially what it does is acidifies the seawater, separating the CO2, which is then vacuumly vented here. And then before putting the water back into the ocean, it needs to return to its alkaline condition, of course, so as not to alter the ecosystem. And then it can return. It is really promising technology that MIT developed here. They claim an energy consumption, as you can see here, which is below 1 megawatt hour per ton of CO2, which is low compared to some of the direct air capture technologies. And they mentioned also a cost that could go as low as $56 US dollars per ton of CO2 capture here. All of that we capture in our database, in our metrics, as well as what projects, for example, in this case, is one, the technology providers are pursuing. So I hope that gave a good overview of some of the interesting projects and technologies. And with that, I hand it back to you, Mike, for your insights about COP28.
Thank you, Christian. That's an impressive database. That's very, very good. I like it. I like it a lot. It's great.
Thanks.
I think that others would welcome the database that we just saw. There's nothing like information being presented on different systems. And here's what I find is that governments are difficult to work with in some ways because in a democracy, they have 4 to 5 years of lifespan, and then they have to get reelected or want to get reelected. And if they're in power, they want to stay in power, and if they're not in power, you want to have power. So it's difficult for politicians to have good information, and databases like this will help, I'm sure. What I find is that I am no longer associated with SAS Power. I'm no longer associated with any government, the federal government of Canada, provincial governments, none of that at all. So I am rather opinionated on what is necessary to be used. And what I find is that there are some elephants in the room, and just what we saw come out of COP28. The biggest thing is addressing the transition out of unabated fossil fuels, and they got stuck on that because Canada, for example, does not want to support EOR. And I disagree with that. I think that you need to you need to clean up whatever your hydrocarbon is for sure, and we have the ability to do that. But you can't cold turkey just say I'm not going to use fossil fuels anymore, and we're going to start next week and or in 2030, which is what, 6 years from now. Like it's just impractical. So somebody has to address the transition of unabated energy. And we need to, and we have the capability to clean up these emissions. Absolutely, we do. So the other thing is that the oil and gas industry gets a bad rap, and maybe it's because they make money. They make a lot of money when the oil price is good, and they don't make so much money when the oil price is not very good, or gas prices are not very good. But the fact of the matter is, in the power generation world, the natural gas-fired turbines have half the emissions of a lignite coal. And the plant that I built, for example, in Saskatchewan in Canada, was 3 times cleaner than a natural gas plant for CO2. Well, that's pretty impressive. But if you got cheap natural gas, it's very easy for a company to say, well, you know what, it's going to stay cheap forever, but it doesn't, because I've been in the oil and gas business all my life. And I know that if something is cheap, you don't drill for it. You just don't. Because if you're not going to get paid for your commodity, why would you have that expenditure? So oil and gas, yes, they get a bad rap, but they are so necessary on understanding how the CO2 can be stored in a reservoir and the transportation of CO2. I got so much information from Norway on the moisture content for carbon steel instead of putting in stainless steel pipelines or whatever. But if you get the moisture content down enough, you don't have the carbonic acid reaction where CO2 reacts with the moisture, and you can eat your pipe out. So either or you can have corrosion in your pipe, which is nobody wants and no regulator wants to see either. So oil companies provide a service of reservoirs that nobody else can. Absolutely nobody else can. So we need to work with the oil and gas industry, and we need a proper transitioning, and we need to educate the politicians that make these incentive programs available to companies that want to build a carbon capture plant and store the CO2 either in a saline reservoir and or use it for enhanced oil recovery and store the CO2 in these depleted oil and gas reservoirs, which is what's happening in the North Sea. So those are really key issues that we need to deal with. And then of course there's direct air capture, which everybody would like, but we cannot even build plants now for natural gas at 4% in these turbines. So to collect 4% CO2 is difficult. And I know just one plant, and actually, Kristen, in your database, maybe you can show us plants or show me later plants that have been built for power generation on natural gas. But just think of it. So you've got 4%, which is a struggle in order to, and you need to concentrate that up to 10, 12, 14% CO2 or higher, because then you can catch and grab this CO2 from that flue gas stream. But in the atmosphere, we have 500 ppm CO2. So can you imagine that's almost like 30 to 100 times more difficult than even a natural gas turbine. So but governments are putting money into direct air capture, and direct air capture has some distinct advantages. One is that you can site your direct air capture at a storage site, or you don't have to use pipelines to transport it, hundreds of miles away. So it has good interest. It's just like when I look at the United States with their Inflation Reduction Act, they have incentives for $160 US for direct air capture. I see in Canada the same thing. They put money into direct air capture. So maybe some good research is going to come out of this, and we'll find some learnings somewhere that make direct air capture applicable, and instead of saying, well, this is for free, or this variable is going to be have no cost to us. And maybe that's the strength again back to direct air capture, where if you can put your plant near surplus energy, then that would help the economics. So we're in a very interesting time right now. And I think that we need to deal with transition. We need to bring the oil and gas industry on side instead of power companies, or instead of oil companies wanting to get incentives from governments that just want to do something right, but don't know exactly what to do. So that's where your database is going to be important to educate politicians, and maybe people like me who have built something that can honestly say, well, that worked, and no, this is not going to work. And maybe that'll be helpful. Because one thing I'll leave you with is this. When we had up to 5,000 people working on our Boundary Dam 3 plant at the peak of operations and construction. And we had hundreds of engineers working, not only at SAS Power, but we had Stantec, which was a great company engineering firm that we hired. And I remember my president for SAS Power coming in to see me, and he said, well, do you need some more engineers? And I said, no, I don't need any more engineers. I think I need a psychiatrist. And that actually is true, because it's a complex situation when you build a plant, and you need champions, and you need champions within your organization to build. You need a champion EPC that's going to actually help and be honest about what they're constructing. And you need an honest technology that says, okay, let's understand what the issues are here, and we can fix them, which is usually what happens in the oil and gas industry, is that when something goes wrong, people work together and fix it. And that's what is going to drive CCS into the future. I'm going to leave it at that, Christian and Eric, and then we can take some questions, please.
Yep. So maybe first I'll start. There was a question about demoing the database. Yep, we'll be sending out this recording. Anyone who'd like to speak to Christian directly and ask questions of the database and have us walk through it, happy to do that. It is a subscription-based database. There was a question about that, if it's open to the public. And then maybe the next question we'll take is to Christian: is CO2 in the ocean an issue for the climate?
It actually is, and there are plenty of studies that are showing that with decreasing CO2 in the atmosphere due to human interaction, there's more CO2. There is what's called ocean acidification, which changes the ecosystem and affects the ecosystem. So it can be, CO2 in the ocean can be a problem. So taking it out from it's certainly not. But what I mentioned when I was talking about the MIT technology, what is also very important is not to contribute more to that problem, because to extract the CO2, you need to do some acidification, but so the technology needs to make sure to return back the water in a state that won't change the ecosystem.
Great. And maybe to Mike, early on, what was so difficult about transporting CO2 in a dense phase, to the question on utilizing the CO2 you had captured or selling it?
Well, I think the biggest thing is compression, and then getting the moisture content down to below 300 parts per million of moisture. So that's the problem. So in a dense phase, you have almost like a 500 times reduction in the volume by making it into dense phase. And then you want at least the depth of your storage site to be greater than 1,000 meters, because then it will stay in dense phase rather than flipping back into gaseous phase, which then it defeats the purpose of storage.
Perfect. Thank you. And then maybe, Christian, we had a question on how do you assess the maturity of the technologies within the database?
Yeah, good question. So similar to how we develop our vendor analysis, how we develop the technology strengths of our vendors. We do also assess the maturity level on the TRL scale from 1 to 9. For that, we base our assessment primarily on the type of plants and demonstration that technology provider has. So whether it's only at lab scale or a pilot plant at small scale demonstration, or if it has one or more full-scale industrial capacity plant. Those are the things we use to assess the maturity. So similar as what I mentioned before, is we do have both things of the projects and the technologies, and we actually use the two together to assess the maturity of the different technologies.
Great. Great. Maybe one other question for Mike. What was the levelized cost of capture, dollars per ton CO2? Can you share anything around that?
Well, the actual plant itself, since it was the world's first, was either the most expensive plant in the world or the cheapest plant in the world. So we had levelized cost of around, our projection was about $117 Canadian, so roughly 90 plus US dollars per ton was our target. And we came in higher than that because we had some issues, and it was mainly on the pads for the turbines, and not so much in the plant, the capture plant, because that came out later. But we did a study with Mitsubishi Cansol systems, and we saw that we could get probably $50 to $60 a ton for a cost of capture on a second generation plant.
Great, great. And Christian, how can I use the database from the perspective of a cement company?
Well, yeah, cement is definitely similar to iron and steel, one of the industries that is exploring more and more carbon capture as a technology. There are a couple of things that could be used from the database that are kind of general for different industries, but I think apply really good for cement. One is the cost calculator, which I haven't shown today, but essentially it does contain also cement as the industry for calculating carbon capture. That to start. Secondly, I think one of the most valuable thing is to see the different projects that are around the cement industry, at which scale they are, what have been kind of the developments, who are the participants, both the EPC companies and technology providers there, learn from those experiences and understand also where that industry is going with carbon capture with the planned projects. And finally, yeah, I believe that the technology part of the database would also show what technology providers have the most experience with that industry, with similar conditions, similar CO2, for example, and hence gain an understanding of who would be some of the first one to partner with if the cement plant wants to invest in carbon capture.
And Mike, I'll give you a little heads up. The last question we'll probably ask is, what do you see as the next value center for CCUS to tap into after tax credits or carbon taxes? But while you think about that answer, Christian, can you calculate the cost of carbon capture for other industries or just the ones we showed today?
No, as I mentioned, cement as well, aluminum, steel, power with their different sub-industries. So coal, for example, which align pretty good, luckily, with the numbers that Mike shared, gas, biomass. So yeah, we have a variety of industries that we have in our cost calculator tool that's based on our projects as well. So the projects we have in the database as well.
Great. And again, any questions we don't get time to answer, we'll send them out via email. We've had a lot of great engagement in the Q&A. And Mike, I'll ask you this last question before we wrap up. What do you see as the next value center for CCUS tap into after tax credits or carbon taxes?
Well, I don't like taxes. And we've got a tax in Canada here that'll go up to $180 Canadian a ton. And it's to me, it's unclear where the government uses the tax dollars. Like, for example, if they're used as a tax to incentivize CCS, good. But it's not done that way in this country. So that's the bad part about a tax and a government being in control of that tax. So incentives are really important, and like what we're starting to see now is the true value of storage and of capture systems, and they will go down, but people have to build plants, and you get to your nth plant, and these things will become affordable, and that's what we need. We need to have affordable capture plants. So, I mean, good databases, people can make good decisions, very important. And then good government support is also critical. But then the government support, they can't continue putting money into CCS forever. So they need to start up the industry. It needs to sustain itself with a carbon price that's realistic, whether it's a tradable global carbon price. And so there's a lot of work to be done. And I'm glad that the United Nations is part of this, because it has to be global regulations so that people can trade equally around the world.
Great. So I want to thank the attendees. Thank you for coming and spending your time today. Obviously, you're interested in this technology and how it can impact the world. Thank you for all the great questions. We will be sending out a recording after this. Look out for future webinars like this. I guess the last thing I'll say is also the database. Part of what we've packaged inside that is the ability to interact with experts like Mike, right? You have the ability within the database to ask us certain questions throughout the course of your subscription and accessing the database, and we'll engage the best expert in the globe for your question and make sure that we're providing insights on top of the data and intelligence that exists within the database. Mike, thank you so much for all the great wisdom you shared and your time, Christian, as well.
And Eric, one
yes.
thing before we wrap up. I know we are at the top of the hour, maybe a few seconds here, but I see Marcus has his hand up. Let's see.
Marcus, did you have a question? Should we take a moment?
Maybe not. Maybe it was a wrong
mistake.
hand.
Okay. Feel free. We'll send out the recording. Ask us any questions. Good to hear, Marcus. Hope you have a great day, a wonderful holiday season and New Year, and look forward to speaking with you all in the future. Thanks so much, Mike. Thanks, Christian.
Thanks, Kristen.
Thank
Eric,
you.
thank you so much. Thank you, PreScouter.
Thank you, Mike.
Okay,
Bye-bye.
goodbye.
Bye-bye.